All right, living environment, true believers and fanatics from across the globe. We've made it to another Hockey Jersey Thursday. Isn't that exciting? Another Hockey Jersey Thursday, and we're right in the middle of the NHL playoffs. I don't know who are you rooting for? If you said Rangers, you're wrong. Anyway, yeah, exciting playoffs, and I think I'm pulling for the Winnipeg Jets. That's why I'm wearing the Winnipeg Jets jersey today. Anyway, yeah, let's do today's Bellringer, and then some of you've got to do the Beaks and Finches lab. All right, let's do that today. All right. Hey now.
Mr. Kovacs class. It's Mr. Kovacs class.
You might learn on time.
It's Mr. Kovacs class.
It's interesting too.
It's Mr. Kovacs class.
And he's super cool.
It's Mr. Kovacs class.
The Finches. Darwin's Finches. Of course, we know. Well, what do we know about Darwin's Finches? That's right. Darwin never really paid much attention to those finches. He gets a lot of credit for work done by other people. But yeah, it's Darwin's Finches. And of course, we know Darwin's Finches are found on the Galapagos. And they originated from one species that landed there that then went through disruptive and directional selection and was able to branch into this tree. Each limb on the tree represents different species, right? At the end of each limb of the tree is different species of finch that's found in the islands, right? And of course, they're different species. You tell me, what does it mean to be different species? Good, right? They're reproductively isolated, that's the key when it comes to species, right? And of course, each of these finches has a beak that seems to be fit the food that they have available on the island. And we learned that it was we've learned how to use the wheel. Good. And we learned it was these people, right? Peter and Rosemary Grant, who studied the finches for lots of years, and they studied the beak sizes of finch populations. And what they found, of course, was there was a correlation between beak size of parents and beak size of offspring, which wasn't surprising. However, what was surprising was interesting was when there was that drought in the mid-1970s, and they measured beak size, and they saw that beak size within a couple of generations increased in average size. It showed evolution in action. It showed natural selection pushing the beak sizes greater, changing the population so that they would be more successful, changing the successful adaptations. That was a big deal. We attribute that a lot to Darwin, but really it was to Grants, right? So by now you should have a good idea of how natural selection works, right? All the different things that go into natural selection. Good, right? And we look at natural selection making new species really in one of two ways. Darwin was a gradualist. He said it was small incremental changes over time, right? But what we've seen is that with some species, it can be quick. And this was an idea put forth by a bunch of scientists in the 1980s about punctuated equilibrium, that it's long periods of stasis. That means stabilizing selection. Then a major disruption quickly splits into two new species. Punctuated equilibrium. It's probably a combination of both, really. Right? So gradualism and punctuated equilibrium. Those are the two models, right? But they both explain where new species come from. And of course, we talked a lot about embryos as being examples, right, of descent with modification, right? We played chicken, pig, or bunny. We studied the embryos quite a bit. What else did we study? We studied homologous structures, right? These bones are evidence of descent with modification. We studied vestigial structures like the whale's hips, appendixes, and then looking at DNA evidence, we see how more closely related organisms have more mutations in common, in their DNA sequences for various proteins. On the regents, they'll probably ask you a question like this, like which two species based on their DNA, or which species is most closely related to the unknown species, right? And then you should be able to look at the DNA sequences and figure out who is who, right? Or they'll be like, which two species have the most in common? Right, so looking at, again, at their DNA sequences. And then you're gonna be asked to be able to measure what's called a cladogram. Cladogram, right, is basically the tree. So the letters at the top are the like species that are around now. And if you follow the lines where they intersect, those are where there was a common ancestor. So common ancestor number 1 was the common ancestor of A, B, C, and D. Number 2 was the common ancestor of B, C, and D, right? Not A. Does that make sense? Right? If we put a 3 here, that would be the common ancestor of C and D. C and D are the most closely related species. They're the most recent common ancestor. So you should be able to read one of these. Which two species have the most recent common ancestor? That's right, D and E. So we're studying a little natural history with Charles Darwin and natural selection. History of life on Earth with Charles Darwin. We're going to look tomorrow at some fossils. Fossil evidence is great evidence. And then, yeah, I was thinking next week, a week from today, is your test on all this stuff. So you better get cracking. All right, let's go.